So yesterday, right, we began with the concept of sample space. Let me just what is this? In other words, just some more words on it, right? It is a there is a very nice expression which I found, mutually exclusive and collectively exhaustive. These are the terms that characterize this omega. So it should be mutually exclusive, obviously, right? One outcome should exclude any other outcome, right? And the omega should be a collection, collectively exhaustive collection. The word collection appearing twice in that sentence, but okay, right? But let me just put the adjectives and leave it at that. So these are attributes of the sample space omega, right? And some very important properties of omega at this point level itself, right? So that we should look at a classification, right? Omega can be discrete or countable. So in this course, right, the words discrete and countable will be synonyms. So what does it mean, discrete or countable? That means i.e. omega is of the form omega small omega 1 omega 2 omega n. Now do we have an upper limit like this omega n, right? So it turns out that in some cases we do, in some other cases we may not, right? So we have another classification here, finite, where there is an n, and we have the case of countably infinite. So, right, we have all of these possibilities both these possibilities in the case of discrete omega, right? The finite case is this most, right, the situation that most of you are familiar with, right? So all popular probability experiments fall in the finite n category, and it also obviously includes compound experiments which we will be talking a lot about, right, such as the rolling of two dice or each trial itself consisting of a pair of coin tosses or a pair of die rolls and so on, right. So as long as the total number of possibilities or total number of elements in the capital omega, which is the sample space, if that n is a finite integer, then, right, the sample space is both discrete and finite. On the other hand, the sample space can be discrete, but it can be countably infinite. Now what would be good, what would be an example of this? Have you people encountered countably infinite sample spaces? I'm sure you're not the first time you're seeing this. What would be an example?
Flip a coin until you get tails.
Yes, the standard example is of a countable of a sample space which is countably infinite is this flipping coin until you get heads. Now you might wonder, why do we need to consider n going to infinity? Because not all coins have probability of getting heads is equal to half, right? You can have that probability of getting heads to be some absurdly small number, right, in which case, right, you might say, well, I might have to flip the coin forever. That means basically you are repeating that experiment, right, that many times till you get a successful result, right, which is in this case a head. And if you count the number of trials that you need to keep doing it till you get heads, you may not want to put a limit on the number of heads that you have to. You may be willing to toss the coin infinite number of times till you get the head, right. So in such cases, right, we model the omega, the sample space capital omega, as having an infinite number of, a countably infinite number of outcomes, right. Well, you still have omega 1, omega 2, like a small omega, which are the outcomes. The outcome number 1 would be head in the first toss, outcome number 2 would be head, omega 2 would be head in the second toss, that is, and so on, right, going up to all the way up to infinity, right. So this is one, right, possibility. The other possibility is that omega itself is uncountable, and right. This is a very important subtle difference which needs to be understood right up front, right. Do we have examples of uncountable omega? Nobody has an answer to that question, it looks like, right. This is what happens when, for example, you have a spinning pointer, right. You spin the pointer and it eventually comes to rest somewhere, right, and you measure the angle that the pointer comes to rest against some reference axis, right, some theta. How precisely do you want to measure that angle? You might want to measure it to an infinite degree of precision potentially, right. So what then would be the allowed set of angles that you are willing to consider in capital omega? Can you say any real number between 0 and 2 pi, or normalize the 2 pi to 1 and say any real number between 0 and 1, whatever, 2 pi or 1 does not matter, but you get the point, right. How many can you count the number of numbers? If it's a problem to say that way, but I can't help it, right. Can you count that set? No, it's not possible to count it, right. One of the fundamental results in mathematics is that the number of points in any segment of the real line, be it 0 to 1 or 0 to 2 pi, is uncountable, is an order of infinity much greater than, or right, much bigger than the set of integers, right. So in such cases, right, when an experiment is designed to model that situation, the number of points in capital omega are obviously going to be uncountable, right, and this is when things get very a little more interesting, I shouldn't say, right. Our standard tools that we use for the discrete situation, they have to be tweaked, right, they have to be modified to be made applicable to this situation, to the uncountable situation, right. So let me write here, e.g. spinning pointer. The other example that you find in books is a dart board, right, which again will be coming to in this course. You throw a dart at a board and then you measure the coordinates of the hitting point, right. Again, or if you don't like the 2D version of it, the 1D version, let's say you're constrained to or you look at just the x coordinate of it separately, that will be a single real number, right. You don't want to quantize that coordinate to just a finite or countable number of possibilities, you want to allow an uncountable number of possibilities, right. So in other words, any portion of the real line, right, if omega is that portion of the real line, or in some cases the entire real line itself, right, such as a noise voltage or something where you are willing to allow, right, the entire collection of real numbers, although it might sound strange to allow minus infinity to infinity, right, but still mathematically in some cases it's more convenient not to constrain, right, allow the voltages that you might measure, even though physically it is impossible to exceed a certain magnitude, right. So in all such cases, right, we invoke the uncountable omega, right, and tools are somewhat different to deal with this situation, right. For the first part of this course, for the first 3 weeks at least, right, we will be focusing only on the countable version, right. We will postpone our treatment of uncountable omega to a slightly later date, right. Okay. But some of the things that we talk about in terms of properties of sets and so on are the same in both, right. So basically this, most of what we are going to talk about will also apply here, right, where the stuff that will not apply I will point out separately, okay. So don't think that whatever I am going to talk about which is with specific relevance to or importance to this countable case is not at all applicable, that is not true, right. So in some sense this is all of this and more in a conceptual manner, so we will have to wait for that, right. Anyway, coming back to some terminology, right. So we have here set theory terminology and probability theory, right. The probability counterpart. So set theory plays a very important role in understanding probability, right, because everything is defined in terms of sets, or probabilities are assigned to sets, right. So let us go through this one by one. So we have of course the sample space. I will start with this, the sample space. What is the set theory counterpart of sample space omega? It is obviously the universal set. Now note that the universal set is the name is specific to a particular experiment, right. Obviously it does not encompass everything in the universe, right, it is just a terminology, right. All of this is with reference to some particular experiment. Then the elements of omega. What are these? These, the probability counterpart of elements are basically the elementary outcomes. This is what you observe on every trial of the experiment, right. You observe one of these. So mathematically of course the same notation is going to be used on both sides of this, right, diagram. It's just terminology that is different, right. So here you have the omega I, or I am not necessarily going to put an I subscript. I subscript is used only for the countable case, right, and since we said this, whatever, this is going to be applicable to all experiments, right, so we just call it omega, right, the small omega, which refers to any outcome, any elementary any element of capital omega which can occur on the experiment, right. Then you have the subsets of omega. These broadly corresponds to the events, right, including omega itself, right. So omega itself is called the sure event, a certain event, because obviously, right, in any experiment something in omega, capital omega has to occur. So how do you say that a particular event has happened on a trial of the experiment, right, if right, an event which is denoted A, B, C, etc., right, an event A for example is supposed to occur, right, if the omega that occurs in that trial belongs to A, then you say A has occurred, right. So it is quite possible for more than one event to occur on any trial, right. So it is the outcomes which are mutually exclusive, not the events in general, although you can have mutually exclusive events also, right. So that's very important, but remember by definition the outcomes are exclusive. One outcome will always exclude anything else. So subsets are the events that we work with, right. So the empty set phi is the impossible event, right. Okay. Then disjoint sets. So these are sets which are mutually exclusive, which is not, right, the case for all sets obviously, but some sets turn out to be mutually exclusive, right. For example, getting odd number or even number in a die tossing experiment, obviously you cannot get both at the same time, right. So here in set theory you have a terminology here, in probability theory they are mutually exclusive, which we will abbreviate to ME, right, mutually exclusive events, right. It is very painful to write it out all the time, so we will need acronyms for things that we use a lot, right, mutually exclusive events, okay. Then intersection. Of sets. So if two sets A and B, right, intersect, that means that they can both occur together, they can, right. So if both sets occur, A and B occur on a certain trial, then you say that the joint event has occurred, right. So the intersection always refers to a joint event. Right. So these are the most important, most commonly occurring. Now let me see if I can add the union has the same terminology in both set theory and in probability also, right. So in fact it turns out that, okay, so we can write that also, union is basically the same. So this is the union event. So here we don't usually keep talking about a set, we talk about events, right. So you just simply substitute, in many cases we can get the probability counterpart by just substituting event for set, right, except in this particular case this term joint is very important to understand, right, because it will come up 1,000,000 times in this course, right. So you better get used to that terminology, right. Right. So this, keep this somewhere so that, right, it's always available to you if you have, and I am going to assume of course in addition to basic calculus for this course that you are also conversant to basic set theory, right. By now I think set theory has made its way to a fairly low level in the curriculum, right. So we don't have time to keep spend too much time on that, right. Whatever set theory we are going to use is going to be very intuitive and basic, right, not the more advanced stuff, right, which is only taught in some mathematics class, and this is not, I repeat, this is not a mathematics course, this is an applied course where we are going to only use the level of maths that we need for getting the results we want, right. So let quickly, right, go through some set operations that we will need, right. We have already mentioned union and intersection, right. So let me keep this with me so that I quickly do it. So we have let me start with equality. Of course I mentioned this yesterday, right. Two sets are equal if and only if they contain the same number of elements, the same elements, not number, I am sorry, right. Right. So any two sets can be tested to see if they are equal or not, right. This will come up in a subtle way in many situations, right. Let me write them out first and then okay, let us go through this one by one. Union, we have already talked about equality. Union is, right, again very intuitive, right. A has some right, A consists of some collection of points, right, in the sample space. B consists of some maybe a different set of points, right. So A union B is obviously a superset of A and B, right, which consists of all the points which belong to either A or B, right, all of you know that. And intersection is only those points which are common to both A and B, right. So all of this again, and when do you say that AB is 5? So when AB equal to 5, then A and B are said to be mutually exclusive. So they, right. So we will not use the word disjoint, right, we will use the word, as I have already said there, mutually exclusive. Then complement, right, whatever is not in A, if you define A, whatever is in omega but not in A, everything is also with respect to omega, remember, capital omega. So clearly AA complement has to be the empty set phi, and the union AA complement, A union A complement is phi itself, sorry, omega itself, right. So note that, right, you can extend this to more than two sets also. If you have A, B and C, you can, as we will do that, but before that let me point out this notation here, AB, right. We find that intersections occur so frequently, right, that we do not want to keep that, right, writing the inverted U all the time. So, right, we drop it and just write AB, which is unambiguously the intersection only, right. Whereas for the union we will keep the U, right. So what it means is this U cannot be used as the name of a set, right. So one letter gone there, but does not matter, right. If we need lots of sets, we can always index them A1, A2, A3 and so on, right. So we are never going to run out of letters to represent sets, right, combination of letters and numbers. Anyway, so what if you add a third set C? This is pretty much what we can do with just a, one set or two sets. What can we do with, if you have three sets, you can talk about combining unions and intersections, right. So let me maybe I'll go here for that. With A, B, C, what can you do? You can do A union B intersection C. I'll just writing it to show, right, this C, which is the same of course in our notation as A union B C, right. So again in this connection let me also point to the classic way of understanding all of this. You can always draw Venn diagrams, right, to make things clear, right. So the Venn diagram which all of you must have drawn in the past, if I have this universal set is this big outside rectangle, right, and and then I have A, B, C like this, some three arbitrary sets. Of course, right, I am not, if the set were discrete it would have points here, but I am not showing those points, right. That is the usual way in which we draw these sets, right. It becomes very cluttered if you insist that the points be shown, right. So we show it without the points. So this A union B C, right, is basically the union of A and the intersection of B and C, right, and by a distributive law what does this equal? It equals A union B intersection A union C. So this is one version of a distributive law. Now I am right, I am going to ask you to verify this for yourselves, right. You can do these operations separately and note that this set is equal to this set, right. You can do the shading and so on and do it just entirely geometrically. As I said, this course is not about rigorous proving of all of these results, right. So what is another distributive law that we can do with ABC? Another distributive law basically is the intersection in front of a union. Here we had the union in front of an intersection. We have also a intersection B union C, which is the same as A. So this here and now, right, it is looking like the distribution of multiplication over addition, which is right. Immediately you will say, well, yes, AB union AC, right, without just closing your eyes. This is what you have been trained to say ever since you saw distribution of this kind, right, from 6th standard or whatever. So this is basically a distributive property. So both these distributive properties will be helpful, right, and useful. Then of course you have the commutative associative properties of union and intersection. I am not going to, that those things are, so A union B is always equal to B union A, then A union B union C, you can do the union whichever order, right. So let me just simply just say commutative and distributive properties, right, commutative associative properties, right, of union and intersection, right. This is something I do not even want to, right, say in any more detail than this, right. And then we have as a last maybe collection of things that we need to keep in mind are the De Morgan's laws. What are they? AB complement, there are two versions. AB complement is what? So AB complement is A complement union B complement, right, and the other one, let me write it first and then we can look at both of them. The De Morgan's law number 2 would be A union B, the whole complement. This is what I wanted to say, A complement intersection B complement, right. If I make a small mistake, please get up and say, right, I will I will correct it. So clearly here the union the intersection gets replaced by a union, and note that, right, the union gets replaced by the intersection. So this is ACBC, right. So I am not going to spend any time on this because you people are supposed to know this already, right. So with this much set theory, we are pretty much ready to embark into the rest of the subject, right. So these are things that you will be called upon to use at any point in the course. So are we comfortable with all this? If you are not, please review this material from any number of books out there, right. Remember, we are not going to go beyond this. We are going to stay at this level. It comes under what some people call the intuitive set theory, as opposed to some non-intuitive, the next level higher up set theory, which uses more complicated concepts like sets including themselves and so on, right. We are not getting into any of those controversies here, right. So here we will not encounter a set that includes itself, right.